Throughout this course to this point, you've had the opportunity to write a lot of functions, a lot of procedures, to explore different ideas, to create algorithms to solve problems. You've also seen a number of algorithms that we've introduced that tackle important problems. And one of the questions we could ask is, are all algorithms equal? Are all algorithms equal? Are they all created with the same kind of performance or efficiency? Or are some algorithms better than others? It's a bit of an odd statement, but it's an important one to ask. And let's set the stage for this. First of all, you might say, look, computers are fast. They're getting even faster. So maybe the efficiency of a program doesn't matter. If we want to understand how efficient a program is, does it really matter if the computers are just getting so fast? Well, while they are, I would argue that so are data sets getting larger. And in fact, as you may have already experienced in some of the examples you've tried, simple solutions may simply not scale well to deal with data sets that are very large in size. So it is valuable for us to be able to have a way of talking about the efficiency of an algorithm, the efficiency of a solution. And that leads to the question, how could we decide if we have a couple of options for a program, which one's most efficient? Now, that is coupled by several issues. And one is, there's a trade-off typically between time as an efficiency measure and space. For example, if I have a program that's going to compute some particular mathematical function, I might decide to pre-compute a lot of values for expected arguments and simply store them away inside of the computer so I just look them up. And in fact, we saw an example of that when we were computing things like Fibonacci, whereby using that technique we call memoization, storing in a dictionary pre-computed or earlier computed values, we could change efficiency. So there is a trade-off between time and space, but for the most part, we're going to focus on time efficiency. Can we characterize how quickly will a program come up with an answer to a set of inputs? And in particular, are there different kinds of algorithms to do that? Now, there are a couple of challenges in understanding that. The first one, as you've already seen, is even given an algorithm, I can implement it often in many different ways. I could implement it recursively, I could implement it iteratively, I might have different choices of things. So there might be a lot of implementations, and I want to separate out choice of implementation from actual efficiency of the algorithm. While there are many ways to implement something, usually there are only a handful of different actual algorithms. That is, mechanical description of a set of steps that I'm going to use to solve it. And so I'd like to separate out choice of implementation from choice of actual algorithm to solve that. And we're going to see some examples in a second. Even with that, I could ask, so how might I measure efficiency? Well, one option is just to time it. Time it on a bunch of inputs and see what the time is like and compare different algorithms based on the timer. We'll look at that and realize there's some challenges with that. The second one, a little more abstractly, is I could count the number of actual operations, primitive things that an algorithm is doing or a program is doing, and use that to compare different implementations or different algorithms. The third one is I could actually abstract that a little more generally to something we call order of growth. And we're going to focus on that. We're going to argue that this is actually the most appropriate way of associating or assessing rather the impact of choices of an algorithm in solving a problem and in measuring the inherent difficulty of solving an associated problem. I haven't defined it yet. We're going to do that in a second. But let's start with the first two to see why they're not quite what I need. As I said, I could just time a program. Here's a simple way to do it. I import the time module into my Python environment. And then when I want to use this, for example, if I wanted to measure the efficiency of this simple little thing that computes Celsius to Fahrenheit, I could start up the clock by just calling that particular method, actually run the algorithm on some number, and then stop the clock right there and look at the difference in time and print out how quickly did it take me to do that. I could do that for a bunch of trials and see how well I do. Problem with this is the following. The running time certainly is going to vary between algorithms, which is what I wanted to measure. But it's also going to vary depending on how I implement it. More importantly, it's going to vary depending on what computer I run it on. Different computers have different speeds, and they won't vary a lot, but it will have a difference in that. And that's really not inherently associated with the problem itself. And finally, the running time is not predictable based on small inputs. I would really have to try it on a wide range of examples to get a sense of how well is this going to scale. Can I use it to predict what the performance is going to be like on a really large data set? So this is not particularly effective because the time varies for different inputs, but we really can't express a relationship between the inputs and the time we see because all these other factors show up, like what's the implementation, what computer am I running it on, and how well will it scale. Okay, let's generalize this a little bit. I said I could also just count operations. One way to do that is to say, let's assume that these steps just take a constant amount of time. Any built-in mathematical operation, any built-in comparison, assigning values to variable names, accessing things from memory. It's actually not a bad assumption to say they all take about the same amount of time. Then what I could do is say, let's just count the number of primitive operations executed as a function of the size of the input. And that would give me a better measure of the efficiency of the algorithm. So in the case of C to F, there's just 3 operations. I've got a multiplication, I've got a division, I've got an addition. And that captures how difficult this task is. It's actually pretty simple. In the case of my little MySum thing here, which is going to basically take in a number and letting I range over the value up to that point, it's just going to add them all up. I can count. I've got 1 operation to do an assignment. I've got 1 operation to get I out, basically from range. And in here I got 2 operations, because remember this is both doing the addition and then doing the assignment. And I'm going to do those 3 operations over the entire loop, which I'm going to go over x times. So in fact, this little function, I could say, has 1 plus 3x operations. And as I vary the size of x, it tells me how this is going to scale. And that's actually a better step. It gives me a way of characterizing the difficulty, the efficiency, the inherent complexity of this little function. So maybe counting operations is enough. Well, it gets me closer. It certainly nicely now gives me something that's independent of the computer, and it certainly is going to vary depending on the algorithm, which is what I wanted. It still depends a little bit on the implementation. It's not so bad, but it doesn't really tell us which operation to count. I could figure that out, but I have to maybe think more carefully about what operations I'm going to count. So this one is a drawback, although not a terrible one. So the nice thing here is that the count based on counting operations is going to vary for different inputs, which is what I want. And I can come up with a relationship between the size of the input and the expected count. And it has the nice property that it really depends on the algorithm, but it shouldn't in fact depend, and it is independent of the computer and is getting closer to what I want. So I'm going to take that idea and build on it. What we know is that timing and counting evaluate implementations. Timing also evaluates the machine, which I don't want. What I do want to do is have a way of evaluating the algorithm, telling how well it's going to scale, and I want to evaluate it in terms of the size of the input. So I'm going to take that counting idea, but abstract it slightly. Before I do that, I need to decide if I want to predict size or efficiency based on size of the input. I have to decide what I'm going to measure as the size of the input. I want to express that efficiency in that way, so that leads me to a choice. Many cases it's going to be obvious, but in some cases the input could be an integer. It could be the length of a list. You basically get to decide, especially when you have multiple parameters, what I'm going to use. For example, if I'm searching to see if a particular element's in a list, probably I want to use the length of the list as the size of the problem and not the size of the element, since I'm simply looking to see if it's present. We'll see some examples of how we use that in a second. But you, as somebody doing the analysis, have to decide what's the size of the input, or better way of saying it, what is the input that matters, and how am I going to measure the size of that as I talk about the efficiency of the algorithm. Different inputs, of course, will change how the computer runs. And so when I talk about the efficiency, I need to think about that as well. Here's a simple little function that searches to see if a particular element E is in a list L. And what does it do? It simply loops over the elements in the list, asking, have I found the one I want, in which case I'm going to return true. And if I go through the entire loop and I don't find it, I'm going to return false. Obvious little searching mechanism. Here's what could happen though. If I'm really lucky and E is the first element in the list, it's really fast. That's the best case. And in fact, I could say, in the best case, how many operations does this take? Probably not all that useful, because I'm usually not that lucky. If in fact the element is not in the list, I'm going to have to go through the entire list before returning false. And that gives me the worst case, the longest amount of time I'm going to have before I answer that. That's going to be a little more important. There's a third way I could measure it, which is just to say, what do I do on average? And on average, I'm going to look through about half the elements in the list before I find it. In fact, if I run a bunch of trials, I would find that out. And so I could talk about the average case as well. Three choices. I could say, what's the best case? What's the average case? What's the worst case? Which one's more important to me? Well, I want to measure this in a general way, and as a consequence, I want to do it basically for the worst case. To give you a sense of that, again, suppose you're given a list L of some length. I can measure it with length of L. The best case simply tells me the minimum running time over all possible inputs. And in this case, it will be constant. No matter how long the list is, I find it in the first element, I'll give you a very quick answer. The average case is a more practical measure. It's going to tell me on average what I have to do to look halfway through the list. But as I've suggested, the worst case, which is the maximum running time, is really the more useful one to have because it tells me what's the worst possible situation I would see. And in this case, that is going to be linear in the size of the list. As that list grows, the amount of time is going to grow equally or at the same ratio. And so that's going to be something that's much more valuable to me. What's the worst case behavior? As a consequence, that's the thing we're going to focus on. So our goal now is to talk about what we call orders of growth or complexity of algorithms. And the goal is we want to evaluate a program's efficiency when the input is very large. How does it grow as we scale the size of the input? We want to express the growth of a program's runtime as the input size grows. So we'd like an expression that says, as I, for example, double the size of the input, here's what happens to the efficiency of this algorithm. I can't always give an absolute bound, or rephrase it. I can't always give an absolute expression for that. So what I'd like to do is put an upper bound on the growth. Say it will grow no more than this quickly as I deal with that. And I don't have to be precise. I'm just going to use an order of growth estimate, not an exact one. And we'll see what that means in a second. As a consequence, we're going to look at the largest factors in the runtime. Which part of the program is going to be the slowest? Which one's going to take the longest to run? And what's the worst case behavior for that? And how do I put a bound on that as I describe the complexity of that particular program? What we're going to see is that we can categorize algorithms into different classes. There are things that have what we call constant running time. That is, no matter how we increase the size of the input, it takes the same amount of time, in general, to solve the problem. Things that grow linearly with the size of the problem. I double the size of the problem, I generally double or roughly double the amount of time it takes. Things that grow quadratically or with the square of the time. Things that grow logarithmically, that is with the log of the size of the problem. Things that we'll see later on that grow in what we call n log n time, which are not as bad as quadratic, but a little bit more than linear. And finally, things that grow exponentially. And what you can see here is I'd obviously like, if possible, to have an algorithm that is not in this class, because that's really expensive, but is more likely to be in this class or this class, because those are not bad behaviors. And then now we're going to talk about looking at examples of each one of those classes and how we capture that pattern of behavior.